Okay, my dear students, welcome to the next lecture. Before I move on to the next topic, let me emphasize on one or two points from the previous lecture. This is regarding a second solution, this article at page 467 of the textbook. That is when we are unable to get the second solution from the series method, then we devised another technique to get the second solution, which is described over here at the page I just mentioned. I have also given the detail of this page in my notes and added one more page to my notes to explain the mathematical steps of this article. So you must go through the mathematical steps from my notes along with the added page to fully understand how this formula for the second solution, which is known as the Wronskian double integral formula, was derived so that you can understand these topics. And then you have to go through these two exercises to apply this formula. For example, this one, a second solution of the Bessel's differential equation. As you saw that when n in the Bessel's differential equation is a negative integer, then we will not be able to get the second solution from the series method, but then using this formula we just derived, we can find the second solution, and here are the steps, and you can find more detailed mathematical steps from my notes. Okay, now we have completed the talk about the solution of the homogeneous differential equation. Now let us discuss the non-homogeneous differential equations. So, what are the non-homogeneous differential equations? These are the differential equations which possess a source term on the right hand side, so that the right hand side is not zero. For example, this equation 8.99 del square psi is equal to 0, that was the Helmholtz equation. But if you have the right hand side as non-zero term, then this becomes the non-homogeneous differential equation. Okay, I will turn to my notes for this topic. So let me display my notes before you so that you can derive a formula to solve the non-homogeneous differential equations. Okay, so this is the relevant page from my notes for today's lecture, page number 27, non-homogeneous equations. The series solution and the various double integral provide the most general solution of the homogeneous differential equations of order 1. The most general equation of the non-homogeneous differential equation is written as y double dash plus pxy dash plus qxy is equal to f of x, where f of x is a source term and the solution of the homogeneous part has two solutions, y1 and y2, but the most general solution will be given by a combination of y1 and y2 and yp, which is the particular integral or the solution of the non-homogeneous differential equation. So where y1 and y2 are solutions of the corresponding homogeneous equations and yp is the particular solution linearly dependent on the same term f, on the source term f of x. Okay, a linear combination of y1 and y2 can be written like this, that yh is equal to c1 y1 plus c2 y2, where c1 and c2 are constants. Now if y1 and y2 are the solutions of the homogeneous differential equation, then yh is also the solution of the homogeneous differential equation. Let us now derive the formula for yp. Let us assume that yp is equal to v1x plus into y1x plus v2x into y2x as written here, equation 5.19. Okay, now what we have done here, we have replaced the constant c1 and c2 by the polynomials v1 and v2. This is because now we are moving to the solutions of the non-homogeneous equation, so we have to replace these constants with these polynomials. So that's why this technique is called the variation of constants or the variation of parameters. Okay, so assuming yp as written here to be the solution of the non-homogeneous differential equation, let us now take the derivative of y dash p, which is equal to v1 dash y1 plus v2 into y1 dash plus v2 dash y2 plus v2 y2 dash, and here equation 5.20 is written to rearrange the previous equation. Now we have got four terms, so if we now move on to this second derivative of yp, that will include 8 terms and the problem will be lengthy. So what we do here, let us assume that this term, these two terms collectively is equal to 0. So we assume that v1 dash y1 plus v2 dash y2 is equal to 0. So with this assumption we will obtain our solution of the non-homogeneous differential equation. So don't worry about this assumption as long as you get the solution that will serve our purpose. So the final solution will be obtained by taking the second derivative of yp. So this is the second derivative, this is the first derivative and this is the second derivative, and as soon as we replace the values of yp and y dash p and y double dash p into our differential equation, this differential equation, we get this equation. So you can see the mathematical steps here. So this equation is then simplified to this equation, page 25. Okay, and we have rearranged this previous equation into this particular equation, and we notice that v1 dash y1 dash plus v2, this equation then reduces to this v1 dash y1 dash plus v2 dash y2 dash is equal to f of x, because rest of the terms will be cancelled and you will be left with this simple equation. Okay, so we have equation 5.24 and the previous equation, this one 5.21. In these two equations we have v1 dash and y2 dash. As you see, v1 dash and y2 dash is present here, and it is also present in this particular equation. So if we can find, if we solve these two equations, 5.21 and 5.24, for v1 dash and v2 dash, we get the value of v1 dash is equal to this and v2 dash is equal to this. Okay, so this is the denominator is the Wronskian, so that's why I have written in W y1 y2, that is the Wronskian of the differential equation with solutions y1 and y2. So these are the values of v1 dash and v2 dash. Now if we can integrate these two equations, we will reach to v1 and v2, and then writing the values of v1 and v2 over here in equation this equation 5.19, we will determine the value of yp, which is the solution of the non-homogeneous differential equation. Right, so this is what we have done here, and we get the integration of v1 dash equal to this, and the integration of v2 dash equal to this, and that gives us the value of yp as minus y1 y2 fx w y1 y2 dx plus y2 integral y1 into fx over w y1 y2 dx. So that is the formula by which we can find the solution of the non-homogeneous differential equation, and we have applied this formula over here. This is the equation x square y double dash minus 2xy dash plus 2y is equal to x log x, and we have converted this equation into the standard form in which the coefficient of y double dash must be 1. So we will have to divide this equation by x square to get this equation. So mind you, you can only find the values of px, qx and fx when you put the equation in the standard form. That is, whatever is the coefficient of y double dash, you will have to divide your given equation to reach to the standard form of the differential equation, and then you will be able to write px, qx and fx. And in this equation, px is minus 2 over x, as you can see here, qx is 2 over x square, and fx is log x over x. So this is, now we find the solution of the homogeneous part by putting the right hand side is equal to 0, and this is the homogeneous part of the differential equation, and the solution, the two solutions of this equations are y1 is equal to x and y2 is equal to x square, and from here we find the Wronskian. This is the Wronskian which is y1 y2 y1 dash y2 dash determinant, and this comes about to be x square. So you can see the detail from my notes. Okay, so once Wronskian is determined, then you apply this formula of the solution of the non-homogeneous equation to complete your solution. And similarly, one or two more examples are solved here. This is example on page 27, and then I would suggest some homework, because we have completed the theory of this chapter. So let me show you a small page which gives you the homework on this chapter. Okay, now this small page has also been added to my notes. Let me show this page over here. Okay, this is the page for homework. So after completing this chapter, you must go through all the examples done in the book and my notes. Number 2, do exercises 8.4.1, 8.4.2, 8.5.4, 8.5.5 and 8.5.7 from the textbook, and to look for the hints to solve these exercises, you can consult this book, Mathematical Physics by Gupta, which is available, and you will find most of the steps towards the solutions of these exercises. Okay, so that's all about this chapter on differential equations, and we will start a new topic and a new chapter from the next lecture. Okay, thank you very much.